we had discussed transconductance multiplier and its applications. I would like to point out here that for the communication application of the same multiplier, there is no need to use the precision multiplier as such. You can see the basic block comprising of the pair fed by V y, and there was a transconductor converting V x into differential current feeding onto a diode that can be removed. Specifically, when V x and V y in communication normally happen to be very small voltages of the order of few tens of microvolts or something. For such values, there is no need for conversion of the voltage to current. That kind of conversion automatically occurs for the small signal equivalent circuit of the device itself within this. So, there is no special need for conversion. So, directly the signal can be fed to this block, which we had seen as the output block of the precision multiplier. Here again we can get rid of that R y resistance and make use of the fact that when we apply V y here, okay, this V y divided by twice R e of the transistor itself will convert it into a current. Okay. So, this particular structure therefore is going to be I naught here, and current here is going to be I naught plus V x divided by 2 R e of these two transistors, and I naught by 2, and I naught by 2 minus V x by 2 R e. So, that the total current is I naught. Earlier we had been using in series with this arrangement a capital R y, which is not there, that is removed, because this itself is a small signal. Okay. So, basically this is converting the voltage into differential current of this type, linear. Okay. And then as far as these are concerned, this is V x, and V x is being fed to this differential amplifier whose current operating current is this. Therefore, the transconductance of this, if it is G m, okay, which is again V x divided by 2 R e of this, okay, 1 over 2 R e is the transconductance. Okay. So, that is why that transconductance is being varied by V y here. So, that is why this whole structure is basically called a transconductance multiplier. Even though that was not apparent in the earlier precision multiplier, here for the small signal situation you can clearly see that it is nothing but a differential amplifier whose gain, if it is G m into R c, okay, this is the differential gain, okay, G m into R c, where G m is R e of this transistor or that transistor depending upon that. So, G m 1 into R c or G m 2 into R c. Okay. So, this particular thing is going to be I divided by V t, where I is the operating current and I in turn is controlled by another voltage V y. So, output is this into V x, and since I is itself dependent upon another current here, right, we can get that as I naught by 2 plus V y by 2 R e in one case, okay, and I naught by 2 minus V y by 2 R e in the other case. And if you take the differential output, okay, again the constant part will vanish and you will get that as a product of V x and V y. So, this is the basis of this kind of multiplier, I naught by 2 plus V y by 2 R e. Okay, this is the current going here. Half of this will be the current going in this as well as this, right, half. So, half, okay, that is the current in each one of these. Okay. So, that current, okay, divided by V t, okay, into R c, okay, is the gain, okay. That is the current, divided by V t into R c is the gain of 1, and another one is half I naught by 2 minus V y by 2 R e into R c. So, when you take the differential output, this minus this is what is got. Okay. So, this into V x is the output, this into V x is the output. Okay. So, if you take the differential output, this minus that. So, you get this constant term or the feed through term getting cancelled, okay, and you get an output which is dependent upon V x into V y. This is the name attributed to it, this multiplier, that is the transconductance multiplier, and this is normally called, this itself is available as an IC, just this part. This is a communication IC which is called balance modulator, it is one of the applications of the multiplier, or demodulator, balance modulator or demodulator or mixer. It is also called phase detector. Okay. So, this block is commonly used as a phase detector, balance modulator, demodulator and mixer in communication application. This circuit by itself can be used up to hundreds of megahertz, okay, without any problem. So, this is a common communication IC. Let us look at it in a fairly detailed manner. We know that as far as the output is concerned, it is going to give you a product V x V y by V r, right. So, and now this V r is no longer 10 volts, it is okay, going to depend upon I naught, okay, and this R c etc. Okay. So, as an exercise, I would like you to find out the value of V r for this structure. We already have shown that output is proportional to V x into V y. We have also shown you how the output can be evaluated, right. So, please find out the value of V r, which is going to depend upon I naught and R c. Now, as far as it is also going to depend upon V t, right, of this whole thing. Now, this particular circuit is also called XOR gate, digital, right. That is, when I apply A here and this is B, output will be exclusive or A B bar plus B A bar. Let us check that. That is, we must have, let us say, A here and B here. Let us say A is high, B is high. Okay. A is high and B is high. Then what happens? You can see here, this is positive. So, this current is diverted to this transistor. So, this is the path current is going to take. Okay. And this is positive. So, this current I naught is going to be diverted here, and this is going to be off and this is going to be off, right. So, the entire current is going to flow through this I naught. Let us investigate what happens to this side. Since this is off, this entire thing is off. So, this 0 current flows. So, output is going to be VCC here. Here it is going to be, this is VCC and this is VCC minus I naught RC. Okay. So, if you take the output as this one plus and that one minus, okay, it will be this minus that will be minus I naught RC. So, let us put the output as minus I naught RC. It depends upon this thing. If you take the V naught as this is. So, next, if B is remaining the same, A is changed, right. Let us say A is 0, B is 1, right. That means A is changing the polarity, this will be plus and that will be minus. This current has already come here because this has remained the same. This current is now going to pass through the other transistor. This entire structure is off. So, this polarity will now change and here it will be VCC minus I naught RC and this will be VCC. So, this is going to be I naught RC. Now, we will retain this as 1, okay, and this is going to be changed to 0. So, this is going to be plus and this is going to be minus. This is the state. So, when this is plus, this is minus, current is going to this total I naught, right. So, I naught is going to flow through this. And this is plus, this is minus. So, this is plus. So, the current will flow through this like this. So, this will be retaining low and that will be high. So, output will be again I naught RC. Now, this is 1 and this is 0 and this is 0, right. That is the last thing that is left. So, this is changed over to plus and minus. So, already current has gone over here, right. This is plus and this is minus. Okay. So, this plus is going to be transmitted to this now. So, the current will be shifted to this and it will come here. So, it will be minus I naught RC. So, you can see that only when you have A bar B and B bar A true, okay, either A bar B or B bar A true, output is true, high. So, if you call this as 1 1 0 0, that is the XOR logic. So, you can see that this is nothing but emitter coupled logic circuit, and therefore, this is a high speed circuit. Okay. So, once again, if the signal level here is much greater than tens of millivolts, current switching occurs. Okay. And then you can treat this as a logic circuit and assume that this is a square wave, this is a square wave, and the output is a square wave of let us say if these two are of the same frequency, this will be of double the frequency here, because you know the number of times it changes here, okay. And therefore, this is going to be an XOR gate, which is also going to be useful for phase detector application, linear phase detector. Okay. If this is a square wave and this is a square wave of some phase difference but same frequency, then the output will be a square wave of double the frequency, okay, but not really a square wave, it is going to be a rectangular wave of double the frequency, but has an average which is directly proportional to phi. That we have shown the multiplier, wherein we applied amplitude limited voltages to the precision multiplier and showed that output is going to be a rectangular wave whose average is directly proportional to phi. So, this itself can be used as a phase detector, linear phase detector, as long as these amplitudes are large enough to drive the currents to switching from one transistor to the other, right. So, this has a very important application in what is called as phase lock loop. This particular unit as a phase detector is used in what is called phase lock loop, which we will discuss later. This is again one of the important communication systems. So, we had just now discussed the balance modulator circuit, the communication parlance, it is called also phase detector or balanced demodulator or mixer. And I had told you to determine the multiplier transfer function as Vx Vy by Vr. Okay, Vr will come out to be Vt squared divided by I naught into Rc. So, Vt is equal to Kt over Q. If you follow the same steps that we had earlier indicated, you can get the value of Vr as this, that is as a multiplier. As a phase detector, if it is used, again you can show that the amplitude will vary in the following fashion between I naught Rc and minus I naught Rc. That is what we saw as an XOR gate. So, amplitude varies between minus I naught Rc and I naught Rc, and therefore, this is going to be, let us say, phi, the phase difference between the two square waves, and this is phi minus phi. So, you have I naught Rc into phi minus I naught Rc into pi minus phi divided by pi as the average of this waveform. So, this is going to be I naught Rc into 2 phi, here comes 2 phi by pi minus 1. So, this is the average output if you use the XOR gate as the phase detector. This is important, and the phase detector sensitivity, phase detector sensitivity is nothing but delta V average divided by delta phi. This is the definition for phase detector sensitivity. Change of the average for a change in this thing is nothing but, we will call this as KPD. Phase detector sensitivity, KPD, phase detector is nothing but, if you look at that, I naught Rc to I naught Rc by pi. Differentiate that. So, this is KPD. For the linear phase detector, it is the same, whatever be the quiescent phase at which you are working. So, its characteristic will be looking like this, that for phi equal to 0, it is going to be minus I naught Rc, and phi is equal to pi by 2, it is 0, and then it reaches a maximum here for a phase shift of pi is equal to plus I naught Rc. Thereafter again it will repeat itself. Same thing for lagging phase angle, it cannot make out whether the phase is leading or lagging, right. So, whether it is lagging or leading, it will give you the same output, and therefore, its characteristic will be like this. Linear goes on like this. This is for pi, this is for 3 pi by to so on. So, this much information if you know, you can actually use this as basic building blocks in a variety of communication circuits. Now, we will discuss about other multipliers other than transconductance and log antilog now. The important multiplier that we have already discussed when we discussed class D type of power amplifier is what is also available as a precision multiplier. What is that? If you have Vx and a switch, and this switch is operated periodically, connected and connected to minus Vx, connected to plus Vx for tau, connected to minus Vx for t minus tau. So, it is the waveform is like this, Vx, okay, and minus Vx. Now, if you take the average, you get Vx into tau minus Vx into t minus tau by t. This is the V average of this voltage V naught, okay, V naught average. What is it going to be? It is going to be Vx, okay, into let us say 2 tau by t minus 1. So, now I will vary the so called duty cycle by using another voltage. So, this becomes pulse width and amplitude modulation. This pulse width as well as amplitude, they get modulated by voltages, right. This is the type of multiplier. Okay. So, how do I actually modulate the width? That can be done by using, let us say, Vy, the other voltage, okay, and a triangular waveform along with the comparator. The triangular waveform should have a period of t and it has a peak voltage of Vp, and use a comparator here, and this should be the controlling voltage for the switch, right. So, if this is used for the switch, then you can see that if I draw the triangle here like this and put Vy here somewhere here, this is Vp, and this during this period the output of Vc is going to be high, and during the rest of the period it is going to be low. Okay. So, by using similar triangle principle, this is actually what is going to be Vc. This is going to be high and low. Okay, let us call it minus Vs and plus Vs. Okay. So, this width we will call it as tau, then automatically this is going to be t minus tau. So, if this is tau, then using the similar triangle principle here, Vp divided by t by 2, this is t by 2, that is t by 2, in this triangle is same as this height divided by this. That height is Vp minus Vy divided by tau. Once again, using similar triangle principle for this triangle as well as this triangle, right? This height, which is Vp divided by t by 2, is same as Vp minus Vy divided by tau. So, if you use this, you will get 2 tau by t, okay, equals 1 minus Vy by Vp, or 1 minus 2 tau by t is equal to Vy by Vp. So, you can substitute this there and you get this as minus Vx Vy by Vp, which is exact multiplication of two voltages. So, this basic principle uses a comparator, a triangular waveform generator, okay, and Vx and Vy and switches. So, you get exact multiplication without the property of the device, active device being used. Okay. So, this is very accurate because it uses only switches and comparators. The pulse width and amplitude modulated type of multiplier that I had just discussed is also a 4 quadrant multiplier, where Vx and Vy can be taking any polarity. However, since Vy is the waveform which is switching Vx and the average is to be taken, the switching frequency should be much higher than the frequency components corresponding to Vx, okay, and therefore, this is to be used only for low frequency application, because averaging is required to wait for the product output to be got. Once averaging is involved, you have to wait until the average is created for you to get the accurate value of the product. Okay. So, this particular circuit is usable only for low frequency application. The final multiplier, which now is going to be popular, is using field effect transistors. We had already used bipolar junction transistors and their basic property in designing multipliers, the translinear principle and the Gilbert-Gain cell. Now, how do we use FETs and their properties in order to design good multiplier? We know that FET is a square law device. What does it mean? The current of a FET is going to be, let us say, k times VGS minus VT whole square. This is the enhancement type of field effect transistor that we had discussed in the early part of our lecture. ID, the drain current, drain to source current, is equal to k times VGS minus VT. VT is the threshold voltage. So, this square law principle, how can you use in designing multipliers? One way is, we know that basically if we have Vx plus Vy whole squared, okay, minus Vx minus Vy whole squared, okay, some voltage squared is coming anyway, and Vx plus Vy whole squared minus Vx minus Vy whole squared, if you get the output in the following fashion, okay, then that divided by, let us say, Vr, because that is a voltage. So, if you do this, then we will get Vx squared and Vy squared cancelled, we get 4 Vx Vy by Vr. So, in all multipliers based on the principle of using field effect transistor, the square law device, okay, that is the FET, MOSFET or junction FET can be used in order to obtain this kind of structure, where let us say VGS of a pair of field effect transistors, because UET has to be cancelled, okay, could be Vx plus Vy, okay, and another pair has Vx minus Vy. The currents will be now correspondingly proportional to Vx plus Vy squared and Vx minus Vy squared, and then you can subtract the current, okay, by using a node. So, and you can get a multiplier as an output. This is one method. Another method is a field effect transistor ID is equal to 2K times VGS minus VT into VDS minus VDS squared by 2. This is in the triode region. That is when VDS is less than or equal to VGS minus VT. This relationship is valid. This is valid when VDS is greater than or equal to VGS minus VT. That is in the current saturation region. This is called current saturation region. So, if the field effect transistors are used in the current saturation region, in the triode region on the other hand, it can be used as a voltage dependent resistor. So, in the triode region, it can be used as a voltage controlled resistor, VCR. That is because ID is equal to 2K into VGS minus VT into VDS if I ignore the square law term there. That means, if VDS is very low, I can ignore the VDS squared by 2. Okay. VDS is much less than VGS minus VT. I can ignore VDS squared by 2 and say that it is a linear relationship between ID and VDS, or delta ID by delta VDS is nothing but 2K into VGS minus VT. For VDS which is much less than VGS minus VT, this is valid. Or it is a resistance RDS which is equal to 1 over 2K into VGS minus VT. So, it is a voltage dependent resistance. This property is used in a large number of applications where we need voltage dependent resistors. But the condition is VDS must be much less than VGS minus VT. Why should we have this condition? Why can't we compensate for this nonlinearity? How can we get rid of this VDS squared by 2? That can be easily done if you now see that the FET is going to be used in the following manner. This is VDS, okay, and this is VGS, right, this is G. So, I take part of the VDS and feed it back. That part of VDS I take to VGS is going to be VDS by 2 R and R output. So, I put a control voltage here. So, now VGS here, VGS in this case is equal to VC plus VDS by 2, because I have put a attenuator R and R. So, it is VDS plus VC by 2. If I do this and substitute in the earlier expression, triode region expression here, let us do that. ID is equal to 2K times VGS, VGS is VDS plus Vc by 2 minus Vt into Vds minus Vds squared by 2. So, you can get this Vds squared by 2 cancelled exactly, okay, and you get a linear field effect transistor which is usable in a range which is Vds less than, okay, Vgs by minus Vt, not necessarily much less than. Okay. So, in that region, triode region, you can straight away use it as a linear voltage controlled resistor, right. Linear in the sense the conductance is linear. Okay. So, conductance which is 1 over RDS in that case is simply equal to 2K into Vc by 2 minus Vt. Okay. This is the conductance. This is simply ID by Vds. It is not delta ID by delta Vds in that case. Simply ID by Vds is conductance, it is linear. So, this conductance, if it is used in designing amplifiers, for example, if I use this as my, let us say, conductance for amplifier design, let us say I am going to use this in designing an amplifier like this. R. So, what happens to this amplifier now? This is V naught, this is Vi. V naught over Vi in this amplifier is nothing but, this is a non-inverting amplifier, okay, 1 plus, okay, R by RDS, R divided by RDS, 1 plus R by RDS is the gain of this non-inverting amplifier. RDS is nothing but 2K into, okay, 1 by RDS is nothing but 2K into, okay, Vc by 2 minus Vt, that is all. So, this is the gain of this, that means it is now a linear voltage controlled amplifier. The gain of this amplifier V naught over Vi is directly proportional to Vc. So, that means V naught is going to be 1 plus 2 Rk into, we will call this as, let us say, Vy by 2 Vt, okay, into Vi which is Vx. You get therefore a product of Vx and Vy here. Vi is equal to Vx and Vc is equal to Vy, right. So, you get a multiplier, or of course, non-ideal multiplier. You can actually remove this feed through component by using another subtractor, right. So, we can remove the feed through component which corresponds to 1 minus 2 Rk Vt into Vx, right. So, this has 1 minus 2 Rk Vt into Vx, that is the feed through component, and plus 2 Rk by 2, okay, into Vy Vx. This is the product component, right. So, we can get rid of this by using a subtractor. So, you can design multipliers using such voltage controlled amplifiers also, wherein a field effect transistor is used as a resistor. So, this can be easily done, and multipliers of this type are commonly built in discrete circuit design. This is another interesting circuit which uses FET in the triode region as a resistor. as multiplier. Let us see how it works. There are the requirement is that these two FETs should be identical in their characteristics. That means for the same gate to source voltage, okay, these two FETs will give the same value of RDS. So, that is Ks are the same, Vts are the same. So, if that is the case, this is a circuit which will also do the multiplication. You can see that this, if it is Vx, and if we put a resistance here and this simulates an RDS, then V naught is always equal to, it is a non-inverting amplifier. So, minus R divided by RDS times Vx. Vx can be positive or negative. This field effect transistor is used once again in the triode region, and these are the two resistors which are coming as linearizing resistors, okay, which will give you VDS by 2 in addition to the control voltage Vc by 2. Okay. So, this is for linearizing. V naught is equal to minus R by RDS into Vx. Now, the RDS itself is fixed by another voltage here. Let us call this VA and VB. Right. So, if this is, let us say, R, there is a negative feedback structure here, and if it is negative feedback and this is grounded, this will be grounded. So, the current in this is VB divided by R, and this is at 0 volts. So, the current has to go out here. One requirement is that if this is positive, this has to be negative. If this is negative, this has to be positive. These two should be of opposite polarities, because this current is going and this has to be coming out from this. So, if this is VB by R, the current here is going to be the same as VB by R. Therefore, the resistance, if it is VA divided by RDS in this case, VB by R should be same as, okay, minus VA by RDS, or VB by R plus VA by RDS should be 0. So, that means actually RDS is going to be fixed by this negative feedback circuit in such a manner that whatever current goes, since this voltage is fixed, this RDS will adjust itself. Okay. That means, this Vc will change in such a manner as to adjust this RDS to satisfy this relationship, as long as we provide a positive and negative or negative and positive voltages here. So, RDS is going to be therefore equal to let us say R by VB into VA with a negative sign. Now, this we can substitute there. That RDS and this RDS are one and the same, because they are getting the same control voltage. Okay. So, since they are getting the same control voltage, this RDS is same as this RDS, and therefore, V naught is going to be equal to minus R Vx divided by here minus R VA by VB. So, you get Vx VB divided by VA. So, if VB is Vy and VA is VR, we get a multiplier here. If VB is Vy and VA is VR, we get a multiplier. If VB is VR and VA is Vy, we get a divider. So, this scheme gives you both a multiplier and a divider. Okay. The condition here is it is a 2 quadrant multiplier, because Vx can take both polarities plus and minus, whereas if VB is Vy, okay, and VA is fixed as a DC voltage which is positive, Vy can only take on negative values. Okay. So, this is a 2 quadrant multiplier. That is something that you have to note. Okay. Again, if it is a 2 quadrant, it can be made a 4 quadrant by proper biasing and feed through, okay, and then eliminating the feed through component later. So, these are the basic principles of multipliers that are used in a variety of circuit applications. In the next class, we will discuss how this multiplier, which is voltage controlled amplifier, can be used in what is called as automatic gain control circuit and amplitude stabilization of oscillators. Okay. Automatic gain control or automatic volume control circuit and amplitude stabilization of oscillators. What is the basic principle? We can see here that I have an amplifier whose gain is going to be controlled, let us say. This is the practical amplifier. This is the circuit that we had just now seen. So, V naught, this is Vi. V naught over Vi depends upon, okay, the gain here, which is in turn controlled by Vc. This structure we had earlier seen. Now, I want to maintain V naught constant irrespective of Vi. So, I had to have a means of finding out whether V naught is varying or not. Okay. So, I will sort of rectify and filter this sine wave, and I get an amplitude information from that. That I compare with the reference. If it is, let us say, higher than what I want, I reduce the gain. If it is lower than what I want, I increase the gain. Okay. So, this gain is controlled, so that whatever be the value of input voltage, output remains constant. That is what is meant by automatic gain control or automatic volume control. That requires obviously a multiplier or a gain control amplifier.